right into it. So my capstone presentation started, I'm going to get into that a little bit later on in the presentation, but it started as an infrared astronomy project. So infrared astronomy, I'm just going to go through a couple of introduction slides, which if you've been to any of the other ones, you've seen them three times now. But infrared astronomy is the study of stars, planets, astronomical bodies, just like regular astronomy, but it's done with infrared light instead of visible light. The reason that it is better in a lot of cases is because the infrared light has wavelengths that are a lot longer, right? So infrared wavelengths, but they're longer wavelength than visible, which are shorter wavelengths. So the infrared light interacts less with dust and other particles in space. So as you can see from this picture, this is just Orion Nebula. The left is a visible light image, and the right is an infrared light image. So you can see a lot more stars, just a lot more in general in the infrared picture. So every object in the universe emits infrared. All objects emit all light. Some stars, like blue stars, don't emit as much, but they all emit infrared. This is just a picture of Jupiter. The left is visible, the right is infrared. It's a good example because it's close enough to us that you can get more detailed galaxies and stars besides our sun that are farther away. You can't really get great images or readings from unless you're on one of the telescopes up in space that does infrared astronomy. And part of the reason for that, part of the reason they put them in space, this is just kind of a sidetrack, is just because infrared light is absorbed by vapor in the atmosphere to a certain extent. And so by putting the telescopes in space, and then the ones that are on ground, a lot of them on higher elevations, it cuts out the amount of the water vapor in the atmosphere can affect it. So how I did it, how I went through with this project was using pyroelectric detectors. I'm just going to call them PIR, and that's how I'll use them in the rest of the presentation. How they work though is heat hits a pyroelectric material within the device, causing charges to move, and that is actually the signal that I'm going to see, that I'm going to read when I do the experiment. So I have it up here. I don't have it hooked up for data. I was just going to show you the little motor spinning at the end. But basically what happens is the PIR is seeing light in its field of view, and you get a reading or a signal when something passes over it. It disrupts the light that's hitting it. Otherwise, if it's just looking at a constant light, then it won't change and you won't get a signal. They're good because they're cheap, so I didn't destroy any of them, but we got a couple extras just in case, but they're cheap, and they're typically used in motion sensors. We don't have one here, but the ones that are in houses just on the wall. So the main goals for the year-long project, initially it was an infrared astronomy project. That's what I was just describing to you. But I had to change the basis of the project because of noise values from the device itself. So I'm going to get into that briefly. This was a noise simulation that I did with Mathematica. And this line here is a signal observed, and the not horizontal line is the noise level. So as you can see right down here at around 10 to the minus fourth, that is like the max that we'd be able to observe any sort of measurable signal. And the problem is that at 10 to the minus fourth hertz, that's about 10,000 seconds of data taking of observation, so about 3 hours. The project just wasn't designed for that, so because of that speed bump that we hit, we had to make a decision to, in order for me to be able to do the project and graduate, I had to decide to observe cloud and collect cloud data instead. So that's basically what it turned into. Those were my main goals for the semester since last presentation, including last presentation, was to design a board, build a permanent working circuit, design a fan, figure out how I was going to bring the motor to the fan and the board all together in a complete system, and then actually gather some data on each side, a couple different types of degrees of cloud sky. So then the board, I have it up here like I said, so you can come up and take a look at it after if you want. But I'm just going to run through the schematics real quick. When I scanned it in, I guess the pen I was using wasn't quite dark enough, so it's a little not the best. But you get the general idea. My PIR, the pyroelectric device, is that circle on the far left. It's got 3 different pins. So one is G, one is D, and one is S. G just goes to ground, D is a drain, so where it gets the power from, and then S is where the signal is going to come out of. The signal comes out of the PIR and then goes to my G or gate terminal of the JFET. So this is a different G than the PIR, right? The JFET has terminals GDS as well, but it's oriented differently. And the main reason I used the JFET here was to create high resistance so that the PIR would be more or less isolated from the rest of the circuit. So we have the JFET, and then we have this capacitor here is just to stop DC from crossing over to the op amp, and then like I just said, the op amp itself, and then this little piece down here. Well, a good amount of this circuit actually, Dr. Stott and I weren't able to come up with by ourselves, so we consulted Harowitz and Hill's Art Electronics for it. But the general idea of what this bottom part of the circuit does is it just creates additional feedback for that op amp. I also used a photodiode. So the reason that I used a photodiode was because the PIR gives a signal, but it doesn't give any sort of data on the timing of it. So the photodiode gives a very simple up or down based on whether it's seeing light or not seeing light. And how it works on the board, how it works on the board is they're at approximately 90-degree angles or 180-degree angle from each other, and the fan, which I'll talk about a little bit more, has got 4 arms, each at 90 degrees from each other. So the idea is that the PIR and the photodiode will be underneath the arms of the fan and then out from underneath the arms of the fan at the same time, so that I can see the timing. But this is the photodiode schematic. It's fairly simple. It's much simpler than the PIR. We got one side of the op amp here, the dual op amp. This is the actual photodiode itself, connected to power, and then goes to the second side of the op amp, which has 100 kilo ohm resistor for feedback. And then another problem that I ran into when we were doing this is that this created a lot of oscillation. So the photodiode itself oscillated a lot on the oscilloscope. So that 22 picofarad capacitor just cuts down on the oscillations. So this is the initial plug board. I think I've shown a picture of this before. The main reason I'm showing it now is to compare this to the board that I actually used. So it's just a plug board. It's got a ground and power on both sides. I used this when I was testing the noise levels of the PIR, I used a circuit similar to the one you see here. And when I was testing the amplification, which I talked about last presentation, I used this circuit actually. So it's just a little bit simpler in some ways than the board I actually ended up using, which this is a plan of it. So I don't know how well you can see it or not, but the general idea is the board I'm using is only about 2 inches by 3 inches, and so this is a blown up copy of the layout of it. And the reason that I had to do this and plan it out and figure out exactly where each component was going to be going was because this board doesn't have a specific power or ground strip, right? So it's not like a regular breadboard. I can make any strip, I can make it whatever I want it to be. And then these strips all run horizontally across the entire board. So I used this board to I used this drawing to figure out the placement, figure out where things would fit, and also to figure out, you can kind of see these lines are cuts. So I actually had to make cuts in the copper so that from here to here, for example, would connect. So this is the PIR side of the board, that's the photodiode side. There's a cut in the copper so that they are isolated from one another. The only other thing on this is, I'll just point it out real quick because this is what I'm about to start talking about. This hole in the middle is the hole for the motor. So the motor is going to come up through this board, connect to the fan on the other side. This is the final product. This one on the left is just an example just to show you what it looked like before I did any drilling or before there were any components put onto it. As you can see, the copper just runs straight across the board. How I connected each component to the copper side was by soldering, which was a bit of a learning process because it was the first time I had soldered. And like I said, the board is very small. So the trick is to be really careful and make sure that you don't cross over any solder from one strip to the next, because the strips can't be connected together unless they're supposed to be. But as long as the soldering stays on the individual copper strip that it's supposed to be on, everything works. Is supposed to work fine. So this is from that board that I just showed you. It's just a very short video. It's just going to keep moving so that I can explain it to you. This is this thicker line on the bottom is the PIR. The top line is the photodiode. So I'm just passing my hand over both of them simultaneously. And as you can see, they both react at the same time. The PIR signal is much cleaner than the photodiodes, but like I said before, the photodiode is really only being used for timing purposes. So the signal doesn't matter. It's just, all right, so this is where the fan is blocking the photodiode and therefore the PIR, and this is where it's not. So now I'm at the fan. The fan is pretty simple. It's just made from a filing file, and I cut it out using a protractor. The arms are each 90 degrees apart from each other, and the radius from the center of the circle to the edge of the arm for each of them is about 1.75 inches, enough to cover the PIR and the photodiode, which are near the edges of the board. But the inner wheel, the inner circle, is only a radius of about 0.9 inches. So I made sure, I think the PIR and the photodiode are at something like 1.3 inches. So I had to make sure that the circle wouldn't cover the PIR and the photodiode, just the arms would. And this will be spinning on a motor at about 0.5 rotations per second. So this is the motor. That's the actual motor on the left there. It's different than the initial motor that I tried to use. The problem with the initial motor was that it just wouldn't go slow enough. So I had to buy, the physics department actually had to buy a new geared motor. And it worked out because the geared motor was a little bit bigger, the axle was a little bit bigger, both in length and in width, which helped to make it easier to manipulate it and figure out how I was going to attach the fan to the motor, because it had to be attached in a way that wasn't permanent. Because the motor's axle goes up through the board, if I ever had to take the board apart, I have to take the fan off. And so how I accomplished that with the help of Vic was I got a spacer nut, which is this bit here, and that spacer nut is a 1/4 inch, so it fits onto the axle of the motor, which actually already had a hole in it. And so by fitting that spacer nut onto the axle and drilling a hole in the spacer nut, I was able to take just an M3 screw, which is just a measurement little screw, and put it through both the spacer nut and the hole in the motor axle, keeping it steady. And then the fan is just attached to the spacer nut with super glue. Sorry. This is just a very simple knob. What it does is it takes power from the battery, that voltage runs through the knob, and then the knob controls how much voltage I send to the motor. The reason I had to do that was because it's a DC motor, so the speed that it turns is directly related to the voltage running through it. So this is the complete system. Picture there, real thing there. It all came together fairly well. One of the bigger problems we had towards the end was actually figuring out how to mount it. That is just Victor and I thought it was just a big piece of PVC that I drilled a hole through, which the motor could fit into. It's not secured by any means on the inside of it, but that's okay because, like I said, it's only turning about a 1/2 rotation a second, and with a paper fan on it, it's not really going to be creating any type of torque to twist the motor within the stand. The main reason that it had to be used was because the PIR detects motion. So it has to be able to be left and sat by itself so that it will just collect data and not, because if you just pass your hand over it, it's going to collect false data. All right, so finally some data. These are just 2 examples of a couple different runs that I did. I tried to do them on different days, and these actually came out to be the best ones to look at to see the difference. So the top here and the top here are both PIR signals. This PIR signal is from close to sunset last week. One of the days it rained during the day, and then towards sunset it actually got a little bit clearer. So the cloud cover was fairly light. This signal is from a much heavier cloud cover and possibly lower as well. The main point that I'm trying to just show you guys here is the difference. So this signal is a voltage swing from peak to peak, from upper peak to lower peak. Same for up here. The signal is much smaller. They've both been amplified by 15 decibels, so they're both on the same scale. But this signal is much, much smaller because it's picking up less infrared reflection off the clouds versus this signal where you're getting a lot more infrared detection. Then these 2 bottom parts here are just the photodiode. Like I said, the only reason that they're being used is for timing purposes. So besides that, the signal itself is not very important. So the math, what I'm calling future work, for a reason I'll explain to you, but I've already explained briefly, is so we have a couple of equations. So once we have the power, so what's gonna happen is the voltage that we get from the signal is directly proportional to power. So power equals area times flux, where flux is sigma t to the fourth. In this case, our temperature is going to be T effective of the cloud. So that's T ground minus about 30 degrees Fahrenheit per 1,000 feet. So then, using that equation for flux, can go down and go to our next equation for power, which is power equals alpha h squared times flux. That power, the alpha h squared, is the area, but it's related to the field of view of the PIR. The field of view information is in the data sheets, but because I wasn't able to get enough data to actually acquire a calibration for the device, it wasn't very useful just yet. So like I said, the power equals alpha h squared times flux, where alpha is related to the field of view of the PIR. The final equation, power equals alpha h squared sigma, where that's Boltzmann's constant, t to the fourth, plus another term, T reflected. So some infrared is going to be reflected from ground up to cloud, and it's going to be reflected off the cloud. The problem is that on the internet or anywhere that Dr. Scott and I both looked, we couldn't find any good mathematical models for this, so that would have to be looked into more. But the idea behind finding the temperature is to find the delta V, which is the signal taken from the PIR, and work backwards to find temperature, to find power, and then the height of the cloud. The end goal is to create a curve for HV, which is height in terms of voltage, from given values of height, which can be obtained from the National Weather Service. You can find how high the clouds are on a certain day where you're observing. But like I said, because there was a lot of small roadblocks that I hit along the way, whether it was the motor not being quite right, or turns out the board is very picky with when it wants to work and when it doesn't want to work. I'm still not really sure why. There was a couple times I had to just replace a bunch of resistors because they just weren't working. And then as soon as I thought I'd get it working, soldering came off from where it was connected to the bottom of one of the components. The problem is you don't know which soldering it is, so you got to go through, test the voltage, test the signal of each component, and then once you finally figure it out, resolder that component. And so just because of those different roadblocks that I hit along the way, I wasn't able to gather enough data to come up with that baseline to calibrate the device, and then be able to do this work. So conclusion was what I did. I successfully designed and built a working circuit. I then integrated this circuit into a complete system, and then collected initial data from the PIR and the photodiode that can be used in future work done that will make the math possible. And that's it. So questions? Yes?
If someone else pick up this project and continue with it?
Yeah, in theory, that's the point. So that's why I had to write the lab report for it. So that in the lab report, I basically go through everything I did, and and everything. And like I said, the math that still needs to be done. But in theory, it could be worked on in the future by another student and probably perfected as well. Just because the board, like I said, has just a mind of its own sometimes and just does what it wants. So it needs to be perfected for sure. Yeah, that would be good.
I would try to at night, use a night result as a calibration to see.
So I was going to try to use the result at night for the calibration.
Yeah.
The problem is, that in order to do that, I would have had to also hook up an LED to the circuit, which, truth be told, I mean, someone who knows how to circuit better than I probably would be able to find space for it, but I just couldn't find a lot of space for the LED. And then the other thing was just timing. So, I mean, I started collecting data probably maybe a week and a half ago, just because of all the problems that came up, and so hooking up the LED and collecting data at night was just something time constraints just didn't allow. Is that it? Trust me, I'm fine if that's it.
Alright, you're not.
All right.
You're done. Thank you.
Thank you.